A fundamental concept in linear algebra is that of an abstract vector space. So the key first step in developing this theory is to understand exactly what a vector space is. In this video, I will teach you the 8 axioms that precisely define this intriguing mathematical object. To start off, a vector space V generally exists over an algebraic structure called a field. It consists of a set along with two operations defined on it. The first operation is, quite naturally, addition. By its formal definition, this operation takes any two elements in the vector space as inputs and produces a unique element that also lives in the vector space as an output. This output element is called U plus V, and since it lives in V, we say that a vector space is closed under addition. The second operation is called scalar multiplication. This operation takes as inputs an element from the underlying field along with an element in the vector space. The output of this operation is a unique element called AU, and since AU lives in V, we say that a vector space is closed under scalar multiplication. So that is the initial setup for a vector space. It is some set with these operations defined on it. This set could be a collection of any objects you can think of. The next requirement tells us how these objects must relate to one another if they are to truly be a vector space, and that is that they must satisfy the following 8 axioms. Axiom 1. For any two elements in the vector space, the order in which you add them together doesn't matter. So U plus V is equal to V plus U for any two vectors UV, and we say that addition is commutative. Axiom 2. When adding together any three elements in the vector space, the sum remains the same, regardless of how the elements are grouped. So it doesn't matter if you add U plus V first and then add W, or if you add V plus W first and then add U. This property is known as associativity of addition. Axiom 3. There is an element called the zero vector that lives in the vector space with the following property. For any element U, if you add 0 to it, it does nothing and you are left with the original element. This zero vector is also referred to as the additive identity. Axiom 4. For any element U, there exists an element V such that U plus V equals 0. We say that V is the additive inverse of U. Axiom 5. For any element U in V, if you take the identity element from the field and multiply it with U, the result is that it does nothing. So we call this element the multiplicative identity. Axiom 6. If you take any two elements in the field and multiply them with an element in the vector space, the result does not depend on how the elements are grouped. So scalar multiplication is also associative. Axiom 7. If you add two elements in the vector space and then perform some scalar multiplication, the result is the same as if you first performed the scalar multiplication and then added. This is known as distributivity. Axiom 8. This axiom is somewhat similar to 7, except now we add two elements in the field first and then multiply with an element from the vector space. Again, we call this a distributivity property. Okay, so those are the 8 axioms that formally define an abstract vector space. Anything that you can think of that satisfies these axioms turns out to be a vector space, whether it's the 3D space that we're all familiar with, or more exotic spaces like the space of all polynomials, or the space of all real-valued continuous functions. The study of linear algebra turns out to be the study of linear transformations that occur on finite-dimensional vector spaces. My hope is that over the next series of videos, I will help you understand exactly what this means, and in the process reveal to you a glimpse of some of the rich, beautiful diversity of abstract vector spaces that make linear algebra such a fascinating subject.